Hello everyone. Thanks Justin for the introduction and giving me this opportunity to talk about my research in today's meeting. So I'm going to talk about the research that we are doing in my research lab, which is regarding the hardware and microelectronics security with a focus on verification, monitoring, and measurement. So as so it doesn't go to the Okay, so as Justin mentioned, I'm Kimia Azar. I just joined the University of Central Florida in fall 2024. I graduated from George Mason University in 2021. After that, I joined the University of Florida for 1 year as a postdoc, and then as an assistant professor, as a research professor for 2 years before joining the UCF. And during this period, I was working on hardware security on both defense and attack side, and most recently I'm more focused on the security verification and monitoring techniques, and this has led to more than 40 publications in top tier conferences and journals, a few best paper nominations and award, and 2 books, 1 book chapter, and 3 US patents, all in the domain of hardware security. So I'm going to talk about a few of them that we are continuing to do in my research lab right now. So if I want to give you the motivation that why we need to do the hardware security and security verification at the earliest stage, I should point out to this specific flow of the IC manufacturing supply chain. So every IC that is releasing to the chip goes through the IC manufacturing supply chain that consists of different stages from design specification, integration, fabrication, packaging, testing, and releasing the chip to the market. However, over time, due to globalization, many stages of the IC manufacturing supply chain has pushed to the offshore facilities, which are known as untrusted entities. So these untrusted entities can do some malicious modification into the design and add security vulnerability into the design. So a different vulnerability may happen during the IC manufacturing supply chain. And apart from this chain, nowadays we are witnessing the ever-increasing trend in the size and complexity of the SoCs. More and more third-party IPs are integrated into the single design to create a system on chip. So the intercorrelation between these IPs become very important, because if the IP is a malicious IP, it can leak the information or the security assets of the design. So we need to make sure the access control policy works correctly, and we don't have any information leakage in the design. So by this, we are witnessing the same trend in the number of vulnerabilities. More and more third-party IPs are involved in the SoC, so the number of vulnerabilities increasing, and we are also witnessing the same trend in the US spending for cyber security and hardware security, which shows that it's necessary to start security verification at the earliest stage. So for this reason, in one of the projects that we have in my research lab, we are using advanced testing mechanism for verifying the system from the security point of view. So specifically, we are working on the methods, we call them fuzz testing and penetration testing. They are very well known in the domain of software. However, we are making them applicable in the hardware domain. So unlike functional testing that use traditional coverage metrics such as code coverage, line coverage, and so on and so forth, so we are using this testing method for security verification. We are writing the cost function, which is a mathematical representation of the security vulnerability, and then we have the security vulnerability coverage. So this testing we are calling self-evolutionary testing, because they have the ability to refine itself in every iteration. Both fuzz and penetration testing use the same procedure. They apply the test pattern to the design under test. However, they gather feedback from the design under test, and then they send feedback to their mutation engine. So the mutation engine, based on the feedback, will decide how to generate the next input pattern. So based on these steps, in a self-evolutionary manner, they can refine themselves and traverse all the corner cases of the design to make sure that there is no security vulnerability in the design. So what is unique regarding this tools that we are using for the security verification is that in most of the security verification technique that we have in the literature, they assume that they have a white box knowledge of the design, meaning that the verification engineer needs to know all the source code of the design in a cycle accurate manner, which is almost impossible in modern SOC. However, in this verification technique that we are working on them, we are assuming that we only have high level knowledge of the design, and by only the gray box knowledge of the design, we can write the security cost function, and based on that, we can verify the design from the security point of view, which has less manual effort. So apart from the verification, even if the verification is 100% successful, and even if the SOC starts securely, it doesn't mean that it will remain secure throughout its life cycle. So for this purpose, we are actually adding the monitoring technique into the design by adding the notion of reconfigurability, meaning that we are implementing the security policy in the design. Whenever the system is in the air and it's running, a new attack may emerge. We call them zero-day attack. So we are reusing unutilized part of the already integrated FPGA into the design that is added for different purposes, such as accelerator, different hardware security purposes, and so on and so forth. So we are reutilizing the unutilized part of the FPGA in order to implement the security policy and monitor the system even when the system is in the field. So whenever it is running, so if we see, for example, one security vulnerability happen, the security policy will send a flag to the processor, and from there the processor will take action, whether block that specific action from the SOC or completely block the malicious IP from the whole SOC. So we are implementing different modules. I'm not going to go through them. However, by adding the eFPGA, we add the notion of reconfigurability into the design in order to monitor the system whenever the system is in the field, in order to be against the zero-day and emerging attack mechanism. So apart from the monitoring system, in another project, we are trying to use transformers and LLM into the steps of the verification. So the biggest obstacle that we have in the IC manufacturing supply chain is the time that we need to dedicate for verification. So in this specific project, we try to combine the transformers and LLM in every steps of the verification that we already have in order to automate the steps of the verification. So we use LLM for different steps of the verification, from assets generation to policy checker, and for example information leakage detection we are using on different prompting technique in this specific project, and we use the LLM for asset generation to information leakage, and using different algorithms such as information flow tracking. So apart from this step, in another project, actually you all probably heard about CHIPS Act back to 2022. So we are migrating from SOC, from 2D monolithic design to 2.5D or 3D ICs with heterogeneous integration. We call them system in package, or SIP in short. So in the SIP, different chiplets are prefabricated in different technology, and they all package together and they are interacting together with a silicon interposer. However, the verification of the SIP is still in its infancy, so we need to come up with some new technique for verification of the SIP domain, which has more handshaking. All the chiplet that we have are in the black box model. We don't have any knowledge of the design, so the intercorrelation between this chiplet is very important. Also, they all fabricated in different technology, which makes the verification even harder. So we need to come up with some verification technique. Right now we just started by migrating some of the verification technique that we already have in the SOC domain, and see how we can make them applicable in the SIP domain. And for the collaboration, based on the project that we are doing in my research lab, I can collaborate with the faculty inside or outside of the UCF who are expert in AI or ML model for data classifiers, transformers, and neural networks. So we are using AI and LLM, as I mentioned, and neural network for automating the steps of the verification for data classifiers. So we need to integrate and combine AI and ML to increase the efficiency of the verification framework that we already have. Also, who are experts in computer architecture, we are using the EDA tool to automate the process of the verification so they can help us for this specific matter. Who are expert in mathematics and science, we know that we have a lot of security assets around the cryptography module, which we want them to remain secure throughout its life cycle. So we need expert in the cryptography module to let us know what would be the asset and what the formal methods, what would be the best formal methods to make sure that there is no leakage for those specific assets. Who are experts in emerging materials right now from the high level point of view, I talked about the notion of reconfigurability that we add into the design for being able to monitor the system whenever the system is in the field. However, new material can be used for adding the notion of reconfigurability, which has a lower area overhead, and add the notion of sustainability as well. So whenever we find some security vulnerability in a critical design, instead of just discarding it, we can reuse it and repurpose it for another purpose. Also, those who are all expert in packaging and semiconductor, as I mentioned in the last slide, so for the post-chip design and verification in the SIP, they can help us to verify the system more easily. So I'm open to all the collaboration and for this new area. So if you are interested in the research that we are doing in my research lab, please feel free to contact me so we can explore more. And I would like to thank all my collaborators and thank you again for giving me this opportunity to talk about my research today. And please let me know if you have any questions.